Morning, everyone. Introduction to this topic. A year ago, Antonio mentioned that on the IMC. We are sitting on a massive amount of spectrograms, and there is not really a ultimate technique to solve this. So Antonio gave it a try, and I also say I will try something. I have basically 14 years of Speclab images per 5 minutes made on the BVS beacon. That's not a record because my friend Felix Verbelen, who is online, I believe, has like 17 years, and he includes also the raw data, so that in fact the spectrograms or details could be even remade. And most of that remains not analyzed or just counted, but there is more in it, of course. After doing this type of project, I found out, in fact, that there was a similar reference in WGN. And afterwards, comparing it, it fitted pretty well, but mine, of course, is much better. The challenge, that's what I gave last year. These are the spectrograms. On the left one, you have planes and 1 or 2 tiny meteors, the vertical lines. Show them, this one and this one. On the right one, you have a few more, and there a bright one, a non-specular reflection. To put it in perspective, time scale is 5 minutes, and that's about 600 pixels. So 1 pixel is half a second. That means that you can't say much below the length, say, of 1 second. If you want to do detailed analysis, this is not a tool. This is meant for some other statistics. In frequency, 200 hertz is a common band. There, I think the resolution is not a problem. What we see here on top, sorry, this is maybe also weak. You see many, many vertical lines. This is almost out of the band. That's because my receiver is bad and it's sensitive to the temperature, so it was hot. Yes, at that moment, there were thunderstorms above the beacon. So in other words, these are definitely not meteors. They are reflections on lightning trails. So the channel also created by lightning also reflects. This is not direct interference from lightning locally, because I am there, 100 kilometers to the east, and there is the thunderstorm. If you look at that in detail, you cannot make a difference with a meteor. Okay, now we're trying to automate that a little bit. And then you come into the domain of machine learning, AI, and all of that stuff. And this is a type of topic that is dealt with. Classification that you might have heard of, seen. Me, the human, the specialist says, this is a cat. The machine, the algorithm, what I decided says, it's a cat. Great, we agree. This is positive and it's true. I say it's a cat. The machine says, no, it's not a cat, and it's false. That we don't want. Vice versa, if I say it's not a cat and the machine says it's a cat, also no good. But if we both agree it's not a cat, great. What's the link with our meteor detection? That was classification. This is object detection. So you're not given something, you have to look it up and see if it fits. All right. I say it's a meteor, machine says a meteor. That's what we want. I say a meteor, and the thing finds nothing. Yeah, well, not good. We lost it. I say it's a piece of a plane reflection. The machine says it's a meteor. That's also what I don't want. And the fourth category, of course, does not exist. If there is nothing, you cannot classify it. It's object detection. So it's along these lines that these algorithms are decided. First to say, here I show the intensity in a scale and a color scale for machine learning, and these techniques, it does not matter. It gets all converted into, call it black and white, to a value, because after all, it's a time signal. But I will keep showing that on the color picture for easiness of interpretation. Right. One historical mistake I find out now I made is that I have these 1 minute lines with these dots. These I have to get them out because everything, otherwise it will say it's wrong. And then I just make a simple interpolation to the left and the right of this line, and it's gone. And there are no artifacts, so it works pretty well. It works better, in fact, than in the other reference I gave where I got more of a problem with that. But at the same time, I have here my time calibration because sometimes there's a pixel that shifts with the minute bound. Okay, let's now see same picture, and now I do a summarization by frequency. So along that line, I summarize that from top to bottom, and here I have a very big peak. And where that comes from, now you have to look really good, but there is a very faint carrier running. And that very faint carrier, although you don't see it, gives in total a very big signal. So that's very easy to identify and say, I overwrite that, I cut that out, it's gone. But pay attention, of course, not to cut your Meteor in 2 pieces, interpolate a bit cleverly. That's one thing. The other view is the time view, horizontally, so by time running. And there you see here, you exceed a certain level, and for that Meteor also exceed a level. This is what happens most of the time in real-time algorithms, like HRO, FFT, they all run, and the signal exceeded, bing, you have a Meteor, and that's it, but without any further detail. Okay, and then of course, if you do the same stuff for a bigger Meteor, you have, of course, a wider band in frequency. Right, I said that already here, another example. That very big blob, of course, exceeded this one, but the very faint ones you cannot detect because it goes into the level of saturation of noise, and then you have to be very careful. Okay, what I'm going to use is this kind of library, computer vision. This thing exists already for a while. It's very stable. You don't need 2,500 algorithms. You need just a few good ones for your problem. And it's widely used, of course, for like identifying objects. So this is a thing I did use. First of all, we do some thresholding because you saw there was a lot of noise in that. We want to get rid of all these little speckles. So you choose a threshold. And let me now see, because that gave also a few days ago. Oh, this is not working. No. I think there's a problem here with the presentation, but can't help it. Anyhow, you see this one is already darkened and the background is much clearer now. Of course, if you threshold it a lot, you start losing information. So there's an optimum, not too little because you have all that noise, not too much, or you lose stuff and you don't get it back anymore. Removing the carrier, that worked pretty well, just by summing up. Could we maybe find something similar to remove these pesky planes that are not straight lines, but more or less? Yes, that problem was solved even 50 years ago by a Mr. Hug, who wanted to remove straight lines on these bubble chamber recordings. Stein also mentioned yesterday that he used the same kind of technique. So yes, we're going to implement it. We will find all these lines, and if they are inclined to the left, it's most likely a plane, and I can cut it out. However, if you try that on my spectrograms, you get zillions of lines, no good. There's a step in between. Before that, this is to make a kind of edge detection where you clean that all up and you remain just with these planes. Then you can say, there I remove the lines. Of course, I should not remove the vertical lines because then I lose my Meteor. So there's again a choice of things. Here's another one where that can be done. Okay, you do a few more tricks. Now you see it moving. Comes to the next thing, the connected components. Each pixel has a component, has 8 neighbors, and these are connected components. And you show them in bounding boxes. That's also where that Stein mentioned. When I apply that, this is what I write. Terrible, huh? Because it's not basically not solved, but I increase now, I play with the size, shape, intensity, how much pixels are in there, and in the end arrive at a very neat picture. Yeah, all correct. Problem solved? Well, yes, for that single one maybe, but you have to run this now on a much bigger set, of course, to test that and tune that. Of these connected components, you can find all kinds of properties, fill factor. You see the good ones and the bad ones, and you see where you have to stop. I use this one. There they are mixed, so I cannot do anything with that. Moving forward fast, in the end, arrive at my results is the recall, as they call it, is like 88% I detect. That's good, but not super. That's achieved before. And I have too many false ones. The ones I find is the false ones turn out to be, that's luck, all to be far from the carrier. So that gives an opportunity to remove them if they are too far. If I do that, I come up with a new recall of 96 point something %, which is really good. Even after that one, the ones that are still remaining are like this, this tiny blob then gets removed. So it was, after all, not a problem at all. Okay. The other thing I didn't say too much about, those are lost. These ones I should have found there. And of course, I find very nice examples in the underdense one. In the end, I have this number of parameters that I play with. I'm about to stopping to do this because you can go on forever tuning that. I could find a few more, but with that, I will start running. And the advantage, of course, is that you have a very consistent method. It's pretty fast. There's not much hardware needed. And that's good enough for analyzing mainly the sporadics during the calm period outside the streams. I have not made a claim about detecting streams. You can also do other types of things to weigh that properly. You have the intensity of the pixels. You can do now all kinds of Meteor work. This is the start of it. The power distributions, also something that was already said. The horizontal wind speed you can derive from the shift in the centroid if you have multiple stations. Not in my case, because my carrier is not, I'm alone in that, and the carrier is not there. For the technicians, this is what's used. We have seen these names already appearing several times. You can have my source. I will make it public for inspiration. It's not a ready package. You will have to dig in and tune it. But then I hope it's of use. I tried another one from Felix without too much effort, and it finds it very well. There's work to do, of course, to remove the lines. But once you start, you have to go on. So that's why I'm not taking too much on it, because you cannot stop halfway. These are my regular people. I say thank you, but most of all to my son. I'm sitting in the same home office with him since Corona for 3.5 years, and which is unbelievable.